Okay? All right. So, based on the poll my assistant has conducted, he has decided to have the help session at Wednesday 4 to 5 in Whittaker's 390A. So that's upstairs somewhere. Okay? So this information is on Canvas. Now, while we talk about Canvas, let me say this again before you. Apparently, some of you got confused where to find stuff. So, files, that's where most of the stuff is, okay? The only other thing you will use here is grades. This is where you will see the scores from homework exams, okay? So files are basically where everything is, okay? You see the handouts, homework, and the figures used in lectures. 3 folders so far, okay? So for example, that help section information is in handout. So there's a handout there that's called ATI for this course, assistant to instructor information. So it's all in handouts. For example, I'm going to give you more handouts today, so that's also in here. Homework policy, that's where you find the homework side, okay? So figures used in lectures, that's self-explanatory, okay? So. All right, so you will see homework number 1 on it, okay? So it's due in a week from today, okay? 3 problems. The first one, it's about the concept of shear stress and its alternative interpretation, okay? So, second, the flow of a falling film. So that's the example we just discussed last lecture, okay? The difference is just that here, it's flowing straight down. It's a vertical wall, so that means beta is 0, okay? All right? So the third one is your chance to practice what we've learned in the last lecture, the shell balance method. So you're going to use that approach we used for solving that falling film problem to solve this problem. Now this problem is similar to that example we used to start our discussion about momentum transfer. The difference here is that, well, the bottom plate is not moving, the upper plate is, okay? So you'll solve for velocity profile, everything else. Okay, the force, volumetric flow rate, and average velocity, maximum shear stress, and maximum velocity, everything like what we've done in that falling film example. Okay, all right? So again, let me remind you, before you work on these problems, study the notes. Try to understand what we talked about, okay? If you do understand what we discussed, this will not take long, okay? All right? So again, this is your practice for exams, okay? So these are the practice problems, okay? There will be no more practice problems for exam, okay? So that's often people ask before the exam, can I get more or get a exam or more examples to practice? Well, this is your practice, okay? If you don't practice now, there will be no more chances, okay? All right? So, which means, for example, you don't have time for this, you copy from others, you don't get a chance to think yourself, okay? Speaking about homework, I do have a different policy about reading homework and exams, okay? Because that's why I asked the students last year, you know, how they would feel about making the homework for practice only. So, well, anyway, they didn't like it. I'm sure you don't like it either. So that's why we still have 20 points. Now, the difference in grading homework and exam is that since really these are for you to practice, nothing else, so that you can do well on exams, okay? I don't really want to force people to practice, to be honest, okay? I don't want to put 20 points or more points there to force you to practice. If you don't want to practice, I feel like it's your decision. However, okay, since students don't like to do things without getting credits, that's why we still have 20 points here. Because my philosophy is for you to practice, right? So that means when the assistants grade the homework, they will be very generous, okay? Which means that you try really hard, you mess up everything here, totally, okay? But you showed that you gave it your best shot, okay? There's a lot of effort that's shown on your work, okay? Even though you totally mess up everything, you will get at least half of the credits, okay? So I do that to encourage you to really just practice on your own before you do anything else, okay? All right? So that's that. Of course, when we grade exams, it's a bit different, okay? So you really have to do it, okay? So, all right? Okay, so this is on Canvas, okay? Define, I did that already, okay? All right, any question about the homework? Okay, all right, so that's that. Now, in the handouts folder, you will find 2 handouts. This is one of them. Here is just a table, not this one. I think there are 2 or 3. Yeah. For some sort of common parameters that you may find useful, okay? For example, the first one here is called the units, these different things we've discussed, okay? Second and third, about some common viscosities of common things like water, air, and stuff, okay? So, all right? So you will find this useful for the second problem in homework number 1. Okay, because there you need 1 or 2 of these numbers, okay? All right, so we'll talk about handout number 2 later. So this is on Canvas 2. Homework and this, yeah, so someone asked me about this. It's part of what we discussed last time. Apparently, you may not be very familiar with what I wrote here. Okay. So volumetric flow rate. So I think I explained this in quite detail. It's about this. Okay. So y this represents the average velocity. Okay. Now, this expression here, if I replace velocity with anything else, like pressure, temperature, or anything that's on the surface. Okay. If you have a surface, okay, there's a physical variable on that surface, whether it's force or anything. Okay. If you want to calculate the average of that physical variable on that surface, this is how you do it. Okay? I think in 240 you may have talked about the average density or something like that. Okay? Anyway, so the reasoning behind this calculation is basically if you have a large surface area, right? If whatever this physical variable is not a constant, on that surface area, and then you select a small area, dA, very small, okay? So there you can approximately consider whatever that physical variable as a constant. okay? All right, so of course you multiply that by the area, okay? Then you integrate over the whole area, okay? It's like sum everything up, okay? All right, and after that, you divide that by the whole area, of course, and then you get the average, okay? So that's the average of whatever you want to count, okay? So that's that. Any other questions if you have studied this lecture? No? Okay, all right. So my office hour is Tuesday, 10:30 to 11:30, which means if you start your homework early, so my homework assignment is always that, for example, I assigned it today, right? So generally after this lecture, you can work on any problem, okay? So this means that if you start early, you can come to my office hour on Tuesday to ask questions about homework or lectures, okay? So if you start Tuesday night, that means, well, you'll have to go to the TAs. I don't want to use the word TA, but the ATIs, help section, okay? All right, just a tip. All right, so there are a few things we still need to discuss about this falling film problem we discussed, okay? So we solved everything. Velocity profile, shear stress, everything, okay? All right, so what's left? Well, so first, we'll talk about the limitations of our solution. The first is that there are no ripples at the air liquid interface. Well, basically this means that there are no disturbances that are causing these ripples, okay? Because there is, then the flow is more complicated, and then our solution doesn't really apply. So that's very simple. Now, the second is that the entrance and exit effects are negligible. Which means that we don't consider the entrance region and the exit region, okay? Now, speaking of this, you know that what happens, when water flows from wherever it came from, whether it's reservoir or from a flat channel, we get to the start of the slope, right? So what happens is that at the beginning, indeed, because before gravity is perpendicular to how it's moving, and now gravity can pull it, right? It does accelerate for some time, okay? So this is part of the entrance effects, okay? What happens is that the gravity will accelerate the water flow, but from what we discussed, okay? Once the water accelerates, that will increase what? The shear stress, okay? The shear stress will decrease that flow. It's like a resistance, okay, from the plate, okay? So gradually, eventually these two will balance each other, okay? So at that time, then the velocity will not increase anymore, okay? So that acceleration process is part of the entrance effects, which we didn't really consider in our analysis, okay? All right? So of course, there are other effects too. What we considered is only the middle part where, everything is moving smoothly and, steady state, and, okay, all right? So this is the second limitation. The third one is that the flow we considered is a laminar flow. Now this is a new concept. So what kind of flow is a laminar flow? Well, to talk about laminar flow, we have to talk about the other flow that's sort of the opposite of laminar flow. So in contrast, the other flow, or the flow, may be turbulent. So basically in moment transport or in fluid flow, there are two types of flows, laminar flow and turbulent flow, okay? So what are laminar flows and what are turbulent flows? This is an experiment about a flow across a cylinder. This is not a sphere. Okay, it's a cylinder in this direction, so the flow flows around it. Now, of course, all the not all, some of the fluid particles are sort of illuminated, okay, by light. Okay, so you can see how they are moving in the flow. Okay. So if you follow these particles, okay, you can see it's moving in very smooth trajectories, okay? So they don't just, moving around randomly. You can see they follow fairly stable and smooth pathways, okay? So this is a signature of the laminar flow, okay? In a way, you can see it's like they move in layers, okay? Right? Okay. So there's a number here that's 1.54. You know what this means later, okay? Finally, in contrast, you can see a flow like this, okay? Now this is a flow that's past a sphere. So this is a sphere. Now you can see part of it is still like laminar, okay? Like there. Okay, but just behind the sphere, and you can see here, these particles, or fluid molecules, they don't move sort of in a very smooth and in a very smooth sort of line, okay, or curve. Here you can see their trajectories will become irregular and sort of very like unpredictable, okay? All right. So you look at one point, you cannot predict, where it's going to end up next, okay? So this is the signature of a turbulent flow, okay? I think I may have more pictures, but remember this number here, okay? 15,000. So before it was 1.54, right? So. This is another turbulent flow. So here, this is a water jet. Okay, so basically, the water was sort of pushed out from a very small nozzle. Okay, all right. So depending on how fast you let this go, if you let it go very fast, it'll become something like this. Okay, this is a classic experiment of about the study of turbulent and laminar flow, okay, or the transition from one to the other, okay, all right. So, well, all right. So turbulent and laminar flow. So, how do we know whether a flow is laminar or turbulent? So For a flow to be laminar or turbulent, there is no one factor that can determine whether a flow is laminar or turbulent. However, there is one very good indicator that is called the Reynolds number. Okay. Now the definition of the Reynolds number is basically the ratio between the inertial force in the flow and the viscous force in the flow. All right, so what's the inertial force and what's the viscous force? Well, the viscous force, that's obvious because, in Newton's law, tau is equal to mu times the velocity gradient, right? So that's a viscous force. Okay, what's the inertial force? Well, this is basically what you learned in physics. Okay, so the force due to inertia, due to acceleration and these things. Okay, all right. So, of course, we know that we also can look at these things from the viewpoint of momentum transport, right? So, in terms of momentum transport, the viscous force will be what? The momentum transport due to molecular interactions, right? Viscosity of things. The inertial force will be what? The momentum transport due to convection, okay? So if you do that, and then you can come up with a formula, okay, to do estimates of these numbers. If you look at the momentum flux due to convection, it's what? Rho, velocity, and velocity, right? Okay? So that means if you use rho and two representative velocities, and then you can estimate the momentum transport due to convection, or you can estimate the inertial force, right? Okay. So viscous force, of course, Newton's law, right? Mu, velocity gradient. So mu, velocity, again, it's a representative velocity divided by the length, you get the gradient, right? Okay. So this is how you estimate this number, which is rho VL over mu. Okay. Of course, it's the ratio between two forces. That means this number is a dimensionless number, no units. Okay, it's just a number. All right. So rho VL over mu. So mention that this V and L, V are representative or characteristic velocities and lengths. Okay. So you can say this is characteristic velocity. That's representative either the average or maximum. Anyway, so it's a typical value for the velocity in the flow field. And L, of course, is the characteristic length. So again, this length is representative of a typical length in the problem. Okay, so later you will see how we can choose these sort of typical values for velocities and lengths. Rho and mu, and they are constants depending on what kind of fluid it is, right? So they're just constants. Okay, all right. So Reynolds number. Now, if you remember the two numbers I've shown you earlier, so for the laminar flow, you notice that value is very small. So that is basically the Reynolds number. Okay, so as small Reynolds numbers, flow tend to be laminar. A large Reynolds numbers, flow tend to be turbulent. Okay, so now of course for this problem that we discussed, for the falling film problem, if you take the characteristic velocity and characteristic length and put them all in this formula, okay? And then the Reynolds number you will come up with is this. 4 times rho average velocity delta and mu. Now, obviously here, the typical length or a typical value for the length scale of the problem is delta, okay? So in this case, that means what? The typical velocity that we should use for this case would be 4 times the average velocity, okay? Now you may wonder why, okay? I can explain this after we discuss our next example, okay? So for now, you just need to know this is the Reynolds number that's defined for this problem. That's the Reynolds number we should use, okay? All right. Now in this case, of course, people have found that if the Reynolds number is very small, like less than 20, for this falling film problem, we will get a laminar flow without ripples. If the Reynolds number between 20 and 1500, the flow is still laminar, but now it's with ripples, okay? And of course, if the Reynolds number is larger than 1500, you will get turbulent flow. Okay? So I mentioned that whether a flow is turbulent or laminar, Reynolds number is just one indicator. It's not the deciding factor. Okay? It's not like if the flow is larger than 1500, you are definitely going to get a turbulent flow. And then at 1499, you're going to get a laminar flow. No, that's not the case. It also depends on other factors. Okay? And one of the factors is what? The surface roughness. Okay? So whether a flow is laminar or turbulent also depends on other factors like surface roughness. For example, if that plate that's supporting the flow, the falling film flow, okay, if that plate is glass compared with wood, okay, and a glass surface is more smooth, it's smoother, right? So, and definitely it can produce less sort of disturbances to the flow, okay? You would expect that, well, you may still get a laminar flow and maybe at a Reynolds number that's a little larger, okay? If you use wood, of course, you may get a Reynolds number that's less than 1500, okay? So surface roughness. And basically, it depends on, in one word or one sentence, it depends on whether you have a lot of disturbing factors in the flow, okay? These disturbing factors could be on the surface or could be in the middle of the flow, okay? Anyway, I guess I put this here just to make sure that you know Reynolds number is a good indicator, but not the deciding factor, okay? All right? Yes?
those like numbers 20 and 1500, those are specific to the falling film problem.
Right. So these numbers, 20, 1500, they are specific to the falling film problem. However, a good number to remember is 2000. Okay. In general, if Reynolds number is less than 2000, you can reasonably expect a lambda flow. Okay. And larger than that, flow will tend to be turbulent. Okay. Again, it's just the reference number. Okay. Okay. Now, of course, you may wonder, still, why when the Reynolds number is large, flow tend to be turbulent. So basically, it's about how these two forces influence the flow. Okay. So the inertial force is like your inner desire to be rebellious, okay? Viscous force is like what? Regulations and rules, okay? Yeah. So when the viscous force is larger, so that means this is dominant, okay? People tend to behave, okay, a little better. So the same with the fluid particles, okay? So when the viscous force is larger, everything is more stable, okay? When the inertial force is larger, that means people's behaviors or the fluid particle behaviors, they are hard to change, okay? If they want to go one way, they have large inertia, that means, well, it's not easy to change, okay? So then, this happens, okay? They move wherever they want, okay? So that's one, okay? All right? So that's the Reynolds number. Now you saw this picture I showed you earlier. That's not Reynolds. That's a different guy. That's George Stokes, who made a lot of great contributions to momentum transport or fluid mechanics. Now his picture is here because he's the guy who came up with the concept or suspicion. Okay, so he thinks that, well, you know, there's different behaviors, different flows. Okay, laminar or turbulent may depend on, you know, what kind of forces are dominant in the flow field. Okay, so he came up with the idea, but it's Reynolds, Osborne Reynolds. He actually did experiments, did the calculations, and you know came up with a number. Okay, and later on, of course, people thought, you know, since he's the one who actually did it, well, he got the honor of getting the number named after him. So now this all happened before 1900. Okay, so long time ago. Okay, so that's the end of the discussion of our first example. So before we move on to the next concept, any questions about this problem? Yes.
Why is laminar flow a disadvantage of our problem?
Disadvantage.
Or you said limitation.
Oh, I wouldn't say it's a disadvantage. Actually, sometimes you want turbulent flow, depending on what you want in your flow field. Okay, I wouldn't call it a disadvantage. Now, it's our limitation. That's because laminar flows are much easier to deal with than turbulent flow. Okay, so there was this guy. His last name is Heisenberg. You can call it a physicist or fluid mechanician. He once said something like, when he sees God after he dies, he has two questions. One is why, I think the first one is why relativity, the theory of relativity. of course, everybody knows that's very difficult to understand. One of the jokes is that, you may have heard of this, one of the jokes is that there were only seven people who understood what relativity was. Anyway, it shows how difficult that is. So he would have two questions for God. One is why relativity, and the other is that why turbulent flow. So basically, it's a very difficult problem to solve if it's turbulent. So laminar is much easier to deal with, and fortunately, that's the only flow we're going to deal with in this class. So, okay. Any other questions? Okay. All right. We talked about Newton's law, right? So far, we've only used Newton's law in sort of like 1D flow, right? Okay, in a very simple form. What if we have a problem in 2D or 3D? How Newton's law will look like? Okay, so that's our next discussion. So Newton's law in 3D. All right, so to talk about this, let me go back and use that example we used in discussing Newton's law. So here, we talked about everything, and we're going to actually solve a similar problem like this one. So now, we know here we have the shear stress tau yx, right? If I choose a small control volume in this fluid flow here, you know that. So if this is the control volume I choose, okay? I call it volume because, in this dimension, it's 1 or something, it doesn't matter. So, okay? So, on this control volume, we have shear stress, right? So on the top, we have that. At the bottom, we also have that. So if I choose this small enough, you can ignore the difference here. Okay? Now, if there are no other forces acting, well, of course there's gravity, but gravity is everywhere, that doesn't cause any rotation of this element, okay? So that's okay. Other than that, if there are no other surface forces acting on this element or volume of fluid I choose, what's going to happen to this fluid element? Rotate, right? Because you can see a force like that, a force like that, it's like a force couple, right? It's going to cause this to rotate. So of course, you can't just rotate, right? Because these molecules or these surfaces, they are kind of in contact or adherent with other parts of the fluid field, right? So as a result, to have mechanical equilibrium, you have to have shear stresses like that. Of course, these are what? These are tau xy's, not y-axis, right? Because the normal direction is in x or negative x direction, and the force direction is in y or negative y direction. So they're called xy's. So basically, that's due to what? So this one is not due to the velocity in y direction. Okay, so because here the y component of the velocity is 0. Okay, this was due to what? Due to the mechanical reaction. Okay. Okay, due to the mechanical moment balance. Okay, so you have to have that to keep this balance. Okay, so that said, of course, the alternative interpretation for the shear stress is what? Moment transfer. So here, not only we have this one has to be equal to that to keep this balance. Okay? So, but you cannot interpret this as what? the y component of the momentum, the transport of the y component of the momentum in the x direction. That's because here the momentum in the y direction is 0. So that means when you see this is not 0, if you want to interpret that from the viewpoint of momentum transport, you have to look at where you do have the momentum first. Okay, so just to let you know. Okay, that's not. But that's not the major point of this discussion. The major point of this discussion is that, well, you have to have another stress there, okay? So that means in the 3D, okay, so this is still 1D, you have another stress component already. In 3D, what we're going to get? Well, in general, for a linear incompressible fluid, Newton's law is written in this way. However, you are not really required to understand this equation I'm writing down. I'm writing it basically because I will show you the beauty of tensor analysis or tensor representation. You will see that, everything is represented in one simple formula here. And unfortunately, to use it, I mean, if you don't know tensors, you have to use it in other ways, okay? Because tensor is not required for this class, okay? So that means, yeah, so this represents a tensor, viscosity. This is the Hamilton operator, or the one used to calculate the gradient, okay? Velocity, that simply represents the transfers, okay? Anyway, I wrote down this to show you the beauty of tensor mechanics or analysis, but to use it, I actually will give you another handout, okay? Anyway, so this is how tensor is written. But of course, in terms of using this in different coordinate systems, what do we get? To do that, let me use the rectangular coordinate system to show you all the components of the stress tensor, which is the cowl tilt, okay? So, as you know, or as we discussed before, a tensor has one magnitude in two directions. That's all because we're talking about a force acting on the surface. So the force has a magnitude and a direction. Of course, the surface also has a direction. One magnitude in two directions. That's a tensor. Now, so in the rectangular coordinate system, let's look at first the tau yx, because that's the one we've discussed before, okay? Tau yx. So remember there, the normal direction of the surface is what? Either in the positive or negative y direction, right? So x, y, and z. So this is, I can consider this as a rectangular prism, okay? So we'll have 6 surfaces to look at. So first, we can look at tau yx. So that means it's either this surface or the opposite surface, right? So let's look at this one. So this surface, the normal direction, of course, whenever we talk about the normal direction, that means outer normal. Okay, it means you go from the inside of the volume to the outside, you get the outer normal direction. So this one points to the positive y direction, right? Okay? So that means if tau yx is positive, it should point to the negative x direction. So that means tau yx on this surface will be pointing to that direction, right? Okay. So remember, we're talking about force on the surface, right? So now we know the surface, okay? So the surface is pointing in the y direction. No problem there, okay? So what's left is what? The direction of the force and the magnitude of the force. So for a force, we have how many components in a 3D problem? 3, right? Force is a vector. So we wrote down one of them, okay? The one in the x direction, okay? Point, if it's positive, it points to the negative x direction. So there are 2 other components. That means tau yz and tau yy, right? Okay? So tau yz, in which direction do you think it points to here? Negative z, okay. So that's the second component, tau y and z. So tau yy. Tau yz is similar to tau yx. It's also a what? A shear stress. Okay. So in other words, a force would shear this rectangular prism this way. Okay, just like tau yx is shearing it that way. Okay. So basically it's like this or that. They're both shear. Okay. All right. So first, for the third component, tau yy, in which direction it points to? Left or right?
Left.
If it's positive.
Left.
Left. It should point to the negative y direction if it's positive. Okay? That's all because the normal direction of the surface here is pointing to the positive y direction. Okay? So all the forces, if they're positive, they point to the negative, the second index there. Okay? All right. So since both tau yx and tau yz, they are shear forces, right? So it's necessary to talk about what kind of force or shear stress tau yy is. Tau yy is not called a shear stress anymore. It's called normal stress. Okay, that's basically because its direction is normal to the surface. Okay, so that's how it got the name. All right, so the directional force or stress is normal to the surface. So it's called a normal stress. Okay, so all right. The normal stress, in terms of the molecular mechanisms for momentum transport, is also a little different from shear. Okay, so for shear, attractive forces are more important. Okay, all right. So, well, I guess in shear, repulsive forces, they're also kind of important. So it's like as long as there are forces independent, there is momentum transport, right? For this one, it's like all the molecules, you know, they move in a line, okay? So this tau yy means either the molecules are pushing on each other to let it go faster if you push on the, so imagine, you know, these molecules are in a line here. If I'm a molecule, if I push on the molecule in front of me, that's going to cause that tau yy. Okay, and also if I pull on them, it's also going to cause that tau yy. Okay, so before it's this kind of force. It's like pulling this way, and now it's pulling this way, or push either way. Okay, all right. So that's what that tau yy is. Okay, that. So. These are 3 components of the shear stress tensor already, okay? So where do all the other components come from? Of course, there are other surfaces we have not looked at, okay? So, well, actually this, well, maybe not. Anyway, so, this surface, what's the normal direction?
X-axis.
X direction, right? Positive X direction. So, now actually you can draw yourself. If the 3 components of the stress tensor are positive, in which direction they point to, right? Okay, so you can draw it. I'll draw it here and make sure. So x, y, because the normal direction of the surface is positive x direction, so xy, xz, xx. So do this with the dotted line because it's going into the wall, okay? All right, so 3 more, right? And of course, the last surface we have not considered is this one. And on there, you will have tau zy, tau zx, and tau zz. Okay? So these are all the 9 components of the stress tensor. So, and we've talked about this already. So these stresses, tau xy has to be equal to tau yx, otherwise you get rotations, right? So, and of course tau xz is equal to tau zx, and tau yz is equal to tau zy. Okay. All right. So there are 9 components, but actually it's like 6, right? Because all these shear stresses, they equal each other. All right. So, okay. So this is the whole stress tensor, 9 components. So you don't really have to know what a tensor is, but you should know how to use these components. Okay. And how do you calculate these components? That's the other handout I was talking about. So it's handout number 2. That's also on Canvas. So on this, you will see the tensor notation for Newton's law in 3D. Okay. Also, I should emphasize that this is, if you look at the book, this is a little different because the book includes the term for compressible fluids like air. Okay. Since in this course, we're not going to deal with any compressible fluids. So that's why you see this simplified version, okay? All right, so in rectangular coordinates, the 6 or 9 components and how they are calculated, okay? You see the difference here for tau yx. So before, it was only this, right? So now you also have this. That's because if this one can cause tau xy, this will cause, if this term will contribute to tau xy because of force or moment balance, then this will contribute to tau yx too. Okay, so that's why you have to. Now, there's a way to actually derive Newton's law in 3D. Why there is such a relationship between all these different terms. But again, because we don't require a tensor in this course, we don't really want to do that kind of derivation. However, you should know that for 3D problems or for any problem that we deal with, these are the equations you should use when you calculate the stresses, normal or shear. Okay? All right, 9 components. Of course, you wonder that there are 3 other surfaces. What do we do? Well, the 3 other surfaces actually, again, because of Newton's 3rd law, okay, and their components are actually determined already by these components. Okay, as long as this is small enough, Newton's 3rd law will dictate that, well, for example, let me draw one of them. This surface here, okay? The surface with the negative x direction as the normal direction. So that will be this surface, right? So on that surface, we'll also have the 3 stress components. Now, of course, the normal direction of the surface points to the negative x direction, right? Okay? So that means, for example, if tau, let me see, that's the y direction. You should have corrected me. Okay. So that's the negative y direction, not the next x, not the negative x direction. Okay. All right. I'm getting older. Sometimes I don't say what I think. Okay, so all right, negative x direction. So that means tau yy would be pointing to the positive y direction, and tau yx will also be pointing to the positive x direction, and tau yz would be pointing to the positive z direction. Huh?
Why are the directions flipped from the right face of the cube?
That's because this is a different surface with a different normal direction.
It's in a negative.
Yeah, so now the surface points to the negative y direction, right?
Okay.
So that means if these stress components are positive, they should point to the positive, whatever the second direction is.
Okay.
Okay? So that means, see, this is yx, right? This should point to the positive x direction, positive y, positive z. That's the definition of the positive directions of the stress we've defined, right? Okay? Okay, so I won't draw the other two surfaces, but you know how they will look like, right? Okay, so do you think we should draw them? No, right? Okay, good. All right, so in the handout, you will see this, right? You will also see Newton's law in 3D in cylindrical and spherical coordinate system, okay? I want to although I won't draw these individual components, but I do want to remind you the definition of the cylindrical coordinate system used in that handout, okay? So in the handout, you look at cylindrical, it's r, theta, and z, right? So what are these three coordinates? Well, if you use the rectangular as the reference, x, y, and z, the cylindrical coordinate system, r, theta, and z, the r direction will be like that. Okay, so basically, in an xy plane, okay, you start from the origin, okay, and then you move away in any direction. That's your r direction. So this has to be inside the xy plane, okay? And of course, the angle formed between the direction in which you're moving and the x-axis, that angle formed is theta, okay? The z direction is the same z as the rectangular coordinate system, okay? R, theta, and z, okay? So, and of course, you look at here, you have r, theta, theta, and z, z, r, theta, theta, z, and z, r. 1, 2, and 3, okay? All right? I do not want to draw this anymore because if you replace this r direction, theta direction, and z direction, you get a volumetric element like this, okay? So of course, r will become an arc. However, theta will also become an arc, right? Because when you move up, sorry, r is still a straight line. It's the theta. When you move theta, it will become arc. So that's the volumetric element in the cylindrical coordinate system. So this rectangular prism will look a little different, but these components, they still look the same. In other words, if this is r, if you're looking at a surface with the r direction as the normal direction, that will be tau r, and this will be tau rz, and that will become r theta. Okay, so same diagrams. Okay, just different indices. Okay, same definitions. Yes.
Does the handout have a visualization of it, even if you're doing class?
Sorry.
Is there a way to get a handout on Canvas, even if we don't do it in class, that kind of goes through that
Oh,
visualization?
sure. I can draw that and put it on. Okay. Now, of course, spherical. It's a little more complicated. Again, we'll use the rectangle as a reference. X, and Y, and Z. So here are the three coordinates are r, theta, and phi. Right? Yeah. So this r is a little different from that r in the cylindrical coordinate system. And this r is still, you start from the origin, okay? You move away from the origin. But now the movement is not restricted in an x, y plane. Now this movement is in any direction. You get it now, okay? It's like you start from here, you move in that direction, that's your r direction, arbitrary, okay? So that will be the r direction. Now what's the theta direction? Theta is the angle formed between the r direction and the z direction, okay? So that's the theta. It's also different from the theta in the cylindrical coordinate system. What's the phi? Well, you project the end of r, or wherever you are in space, you project that point, okay, to the xy plane. You will get a projected point, okay, and also you will get a projected line of that line, okay. So the angle formed between this projected line and the x-axis, that's the phi. So when you look at directions, okay, so the r direction is that direction. Theta direction is which direction? So basically when you vary theta, what's going to happen here? Well, this point will move in that direction, not perpendicular to this line. So that's the theta direction, okay? So for phi, obviously, when you increase phi, what's going to happen to this point, or even that point? The same, okay? When you change phi, what's going to happen? Well, it's going to move in that direction, okay? So there, it's there, okay? So that's the phi, the three directions. And of course, the stresses you will get are r, theta, theta, phi, r, theta, theta, phi, and theta, okay? All right? So again, I'll draw a diagram and put it on canvas. Okay, yeah.
On an exam, would you give us these formulas?
I don't know. So basically, I don't know what problems are going to be on the exam yet. I gave you these equations because they might be useful for our discussions and for your working on the homework problems. Okay? All right? So they look complicated, but it's just math. Okay? So. Yeah.
Why is it the tau xy equals tau yx?
The real reason is hidden in some assumptions about the fact so we mentioned this limitation. So for this to be valid, the fluid has to be linear. Okay? So that means a linear relationship between the stress and whatever velocity gradient we have. And of course, we have multiple stress components and multiple velocity gradients. So they all have a linear relationship. And then we can call this fluid linear. But that does not explain why these two stresses are equal. However, if we start from there and use some tricks we can learn from tensor analysis, okay, you can show that, well, you have to have symmetry between these two indices, okay? So which means these have to be equal as long as it's linear. Unfortunately, we cannot do that. So, however, which is why, that's why I started from here, okay? If you look at this simple, small element, okay? If the fluid is in mechanical equilibrium, which it is in that simple example, to have that, you have to have tau xy, and tau xy will have to be equal to tau yx. Otherwise, there's rotation, and that's not mechanical fluid. So that's a simple way of looking at this. But there are deeper reasons which we cannot really talk about. Okay? 3D. So our next example is, of course, inspired by the blood flow. And that is where all the stress equations in the cylindrical flow system will come in handy, okay? Because now we're talking about the flow through a tube, okay? Of course, you know, the blood flow, whether it's large arteries, small veins, capillaries, they all flow in the tube, okay? So obviously, the cylindrical flow system will be useful, okay? So obviously this is, we want to discuss this, that's because of the blood flow. And of course, other than the blood flow, tube flow is like almost in all the designed stuff, okay? You know, the heating and cooling system, waste disposal. So a lot of fluid flow is a flow through a tube, okay? So anyway, so the results we're going to get, so they're not going to be just limited to the blood, okay? So anyway, it's, that's why we want to look at this, okay? So we have a tube. The radius of this tube so of course, any tube or circular cylindrical tube, there is an axis of symmetry, right? So it goes through the center of the cross section, and the radius of the tube here is R. So as I mentioned before, to solve any problem, we need a coordinate system. So in this case, obviously, the cylindrical coordinate system is the most convenient. So R direction, Z direction, and of course, you know the theta direction, right? So once you know R and theta, and Z, sorry, and you know this direction of the second coordinate theta, right? In this case, which direction it is. Right-handed system. So the theta direction would go from here this way or that way. that's how we form a right-handed system. Okay, it's like X, Y, and Z, right? Okay. Anyway, in this case, in this example, you'll find out that theta doesn't really matter that much, but I thought I should ask you that so that you understand the cylindrical coordinate system a little bit. Okay. All right. So in that falling film problem, what's the driving force there for the momentum transfer, or for the velocity? So what's causing the fluid to flow? Gravity, right? Okay. So what's different here is that if we are looking at blood flow, the driving force is a little different, right? We know it's not gravity that's driving our blood flow through the circulation system, right? So what's the driving force here? Pressure, right? Because the heart pumps, right? The heart squeezes the blood out of the heart. So basically applies pressure, right? Okay. So in this case, the momentum transport is not going to be driven by gravity. Instead, it's driven by pressure. So this flow here, or the flow in the tube, will be driven by pressure. All right. So as a result, the flow is called a pressure-driven flow. Okay. So flow is pressure-driven, and we can use P to represent that pressure. Okay. All right. So this pressure should be a function of Z, right? So at different time points, the pressure may be different. Okay. So. Other than that, we're going to assume this is a very long tube, okay? So that means the length L is going to be much, much larger than the radius of the tube. Now, why do we have to assume it's a long tube? Because if it's a short tube, we have to worry about the entrance effects, the exit effects. If we use a very long tube, we can get rid of this entrance and exit effects, just like the falling film flow. Okay? The reason why we do that, of course, to simplify the problem, because we're not ready to deal with more complex problem yet. Okay? And also, in engineering, this is kind of like a code. Long tube. Okay? They say it's long, but what they really mean is what? It's infinitely long. Okay? When you say it's a long tube, that means you can consider this tube as infinitely long. Okay? All right? Of course, that will give us some, that will allow us to simplify the problems even more. Okay, you'll see why. So I mentioned that, because of this, we neglect that. So. And we're also going to assume the velocity is fully developed. This is like another code word in momentum transfer. Fully developed. What does that mean? Well, what's going to happen is that if you study a tube flow and you allow the fluid to flow into a tube, okay, at the entrance, you will expect that the fluid velocities will be changing a lot, okay, because you just entered a new environment, okay, a new surrounding. So the velocities will change a lot around the entrance. But gradually, as we move along further in the Z direction, in the tube direction, okay? Eventually, the velocity profile will reach a state where it's not going to change anymore, okay? That's called fully developed, okay? All right? So that means in this case, of course, the fluid flows this way, right? So obviously, on the wall here, you have zero velocity. In the center, you may have larger velocity. So the velocity is in the z direction, but it may change in the r direction, right? Fully developed means what? The velocity profile will not change in the z direction anymore. So, okay? So velocity is the z direction, but eventually it's not going to change anymore, okay? So that means it's only going to be a function of r. It's not a function of theta. Why? Axis symmetry, okay? So that's because, you will expect the pressure is uniformly distributed here, okay? You don't expect, because of that, you don't expect any a different theta, right? So basically, no matter how you rotate your viewpoint along the axis of symmetry, nothing will change, right? So it's like you have a tube, you rotate, well, you're looking at the same thing, okay? So that's why it does not depend on theta. Now, how do you know a flow is fully developed or not? I can probably tell you how you can do this calculation. There's a length you can calculate. That's called the entrance length. So that's basically the length you can calculate approximately. 0.113 R Reynolds number. So it depends on the Reynolds number, as you can see. Okay. So this is the longest you will need. Okay. This number, this formula was obtained when you have a uniform entrance velocity, like everywhere is fine. So that's the most difficult for that to become fully developed. Any other velocity profile at the entrance will take shorter lengths to become fully developed. Okay, all right. So for that, you need distance, which means it's the safest distance you need to assume the flow is fully developed. I said I can probably tell you this. That's because that's my formula. Okay, so part of my master's thesis. Okay. Okay. All right. So we'll stop here and we'll finish this example next week.